Today we're going to be looking over the Opticline T3D system. Specifically, we have a setup related to gear measurement. So we're going to look over a few of the features and take a look at the specific measurement strategies, etc. So we're going to run through a couple of slides just to give you an overview of the technology, kind of features that we measure, and then the breakdown of what's currently capable and what's being worked on within the background at Jenoptik. So the system itself, the Opticline system is a optical shaft scanning system. So in the bottom right corner is a principle to the setup of how it works. So on the right hand side there is a illumination, which in this sense is an LED going through a telecentric lens. On the left hand side we have a CCD line sensor. So effectively what we're looking is a separation of a pixel where the light can pass through or it doesn't, and from there we can depict an edge. So using that setup, we're able to, you can see there's the drawing that's got some characteristics. So small radiuses, distances, profiles, angles. You can see all of the other form positions and tolerances. And now we've got the capability using the T3D to look at things like keyways, bore holes, and gears. So it's a nice setup, all enclosed within one, so that we can run through all sorts of different types of measurement strategies. So Jenoptik themselves are making them since 1986, which was the Generation 1 system, all the way up, as you can see, the different types, generations and models. But now we're looking up to the Gen 5.1 system, which is our T3D. So this was the first iteration of the T3D, and obviously there's been some development since 2019 in the software and the capability, calibration, all of that kind of stuff. But the basis now we're running off of that 5.1 generation system. Okay. So currently in the Opticline software, the green items that you can see on the screen are implemented and working. So these are fully functional setups within the system. The yellow features that you can see are in development. So they're within the software package, but the finalized criteria for the actual release of that is still being worked on with Jenoptik. So we've had some involvement with some of our customers in the UK related to these. So if there's anything that you're looking at that needs to be added into the software, we can have those kinds of discussions with you to understand capabilities and the potential of getting that released. Okay. And on the specific feature side of things, so look at things like profiles, radial runout, all of that kind of stuff. You can see the features that are currently within the software and some that are starting to come for our gear measurements for the spline and involute kind of features. Okay. So that was a very quick run through of the setup side of things, as in the system, and what we can do now is we'll hone into some of those specific features and show you how we can program them and the measurement strategy. So I've pre-programmed the component that's in my hand for the gear measurement. So what we're going to be doing is looking at the helical gear at the bottom side of the part. So I'm going to place that into the machine and just click start to let the program that I've written run through. So within this routine, what we're doing is we're taking a couple of roundness measurements. So the roundness measurements are used to create our axis. So we need to understand the rotational axis of the component. Once that's completed, we bring the tactile probe in, and what we're going to do is look at concentricity, the runout, the total pitch error, the adjacent pitch deviation, the pitch deviation itself, and then the toothing width as well. Okay. So what we're doing is we're running through that data set. The concentricity is taken using the optics on the external. So you can see we've got 16.5 micron concentricity error to the axis. So that's the axis of the component from the two roundnesses that I've measured, one at the bottom and one at the top. And now what we're doing is we're bringing out the probe to come and measure the gear feature. So there's a key thing to note when we're talking about gears, especially in the sense of the probe that we've got on the machine. So the probe that you can see here has a larger Z negative length. And the idea behind that is that we can use that probe to come in on the internal of parts. So you can imagine we had a spline on the inside of a component. We've got some external geometries that we'd like to use the system for. And then we want to bring that probe in to measure the internal feature. So that's what the ability of having the longer Z negative probes will help us to achieve. Okay, we've inputted the data for the number of teeth, the module, as well as the pressure angle, and from there the system will be able to calculate the gear specification and we can output our features. So obviously each one of those features is going to have an individual tolerance. So what we've done is I've just applied an open limit. Apart from on the run out, there's a 50 micron max limit, okay? So if we were to review the toothing width, so on the software, if I go to the toothing width now, you can see that we're measuring at 3.5289. And what that's doing when the program's completed is we can take a look at the individual contour of that tooth, okay? So now you can see that the program is completed and we've got a measurement result for all of the features that I mentioned. So if we were to look into the individual setups for those, so we've got our pitch deviation. So we go to our detail contour, we can change our magnification and you can see our pitch deviation for the tooth. If we were to go to the toothing width, you can see within our detail contour, we've got the scan of the tooth as well as the toothing width and the intersection of where that's been taken. Our total pitch error, again to our detail contour, we can see our total pitch error. And lastly, our run out. So when we look at the run out, we can see the run out of the component. So it gives you a little bit of an overview as to how the features are measured. And now what we're going to do is we're going to run through the principle of programming those features. So now we're going to take a look at the programming side of things on the Opticline. So we've got the program window. So on the right hand side, it's asking whether we'd like to run in millimeters or inches. So in this sense, we're going to run in millimeters and we're going to take the contour from the machine. So what's happening now is the machine is going and scanning the part that's in the centers. What we can do is if we've got a nominal DXF file, we can load the program in from the DXF and obviously the features that comes in will all be to nominal to the drawing. So I've selected the area where I'd like the program to be created from. I'm then creating a length position, so our datum position, our LREF, and we've got a hole on the center of this ground surface. So we're going to select that as our valley. So something that's going to help us to clock the rotation. I'm going to give it a name. So we're at the gear webinar. And what we've got now is we're ready to create a program. So the first thing we need to do is to create an axis. So I'm just going to create a roundness feature on the bottom of this ground surface and also at the top of this surface here, okay? From there, we can go to our search tool and we can search for an axis. We're looking for a rotational axis, so R01 and R02. And you can see now we've got our axis 01, which is the axis for the component. Now for us to look, what we're going to do is you can see here, we've got the functionality of our toothing tactile setup. So these are the functions that we discussed earlier within the presentation. So within the software, what we can do is we can select those features and create them from our outside or inside data set. So in this sense, what we're going to do is we're going to start by looking at the toothing width, just to give you a flavor as to how this works. So you can see I've got no data reference, so I can create a new reference, outside toothing, and I'm going to select the center of this gear. Within our TO2, what I need to do now is select the probe that I'm going to use. So we're going to use our special probe, which has got our front-facing probe tip. We've got the number of teeth, so there's 17 teeth on this gear. There is a module of 2.9, and our nominal pressure angle is 20. So from here now, what I can do is I can select measure, and this is going to measure the axis, the roundnesses, as well as that toothing width, okay? So you can see within the software, it's not the most complicated. Effectively what we're doing is we're defining the parameters within the software, and once we've got there, we can reference all of the other features to that data recording, okay? So you can see the probe is following along the gear. You can see that we're measuring a helical gear. So in the beta version of the software that we're currently in, you're able to look at the helix angle. So we can input the helix angle, and from 2 circle measurements, we can calculate that helix angle. So as you can see, our measurement is completed, and you can see that the toothing width is coming in at 3.572. If we were to look at our T002, you can see the data set, and when we come out of our magnification, you can see the teeth that we've measured. So you can see the information we're obtaining. We're getting a nice measurement on all of those teeth for that gear. So what we've done is I've placed the component into the machine. We've started and run the program, so a previous program that we've written with all of those functionality that we showed you before. So now what we're going to do is we're just going to show you the demonstration of running a measurement or creating another measurement on the component. So I can go to my toothing function, and if we wanted as an example to look at, say, the pitch deviation, I can select the pitch deviation. Here I've got the reference that I'm going to refer to, and on the drop down you can see I've got my gear data recording, and from clicking there I can now right click and click measure. And what that's going to do is it's going to measure TO1, which is the pitch deviation. And as you can see now, it's going to run through and measure the feature that we've selected, that pitch deviation. So now that routine is completed, you can see that we've got the finished measurement for the pitch deviation, and you can see that it's coming up at 9.6 microns. So if we were to look at our detailed contour and we were to review the core section review, you can see the step changes in that pitch deviation. So when it comes to reporting, we can output on the Opticline systems to QDAS, CSV, PDF, mini DFQ, and then a mini CSV. We also have, depending on the capability or the need of a client, we're able to export in a custom format. So you can see obviously we've only measured TO1 from our routine, but what we'll have is the features that have been measured. We'll have the graphic on the right hand side with the measured value and the deviation from nominal. We can also edit, so if we went to the edit function, I won't go too into depth into this here, but we can create a specific routine. So if you wanted to see the contour that I showed of that pitch deviation, we could add that into report, click save, and that would save as a standard template for this program and this routine. Okay, so it's a very quick overview of the reporting side of things, the ease of use, and how quick it is to measure a component with that complexity. So that was a very brief overview of the Opticline T3D system. So if you have any questions, please place them into the chat. What we're going to do is review them all at the end of the webinar. So now we're going to pass over to Sensofar, who's going to do a review of the neox system with some gear measurements. And lastly, we're going to look at the COCOS system, which is a new type of gear technology that we're very excited about. So thanks very much for your time, and over to Sensofar.
Hello, everybody. I'm Mireia. I'm a product specialist at Sensofar headquarters, and I'm here today to, first of all, talk about a little bit about the company and also present one of our products and the applications that we can solve within the gears market with that product. So, first of all, Sensofar was founded in 2001 in Barcelona. Our purpose is that we design and manufacture optical surface measuring instruments mainly for quality control, quality inspection, and R&D. Well, here you can see our portfolio. As you can see, it's divided in three main sections. First of all, we have the tabletop solutions, mainly for R&D, laboratories. Then next to it, we have the integrable head solutions. That's more for production, for quality control. And then we also have a set of softwares. Here at the top, we have our own acquisition softwares to control every system. And then we also have analysis softwares depending on the level of automation you want, and also depending on the level of detail you want for concrete manual analysis. So let's review the tabletop solutions. So here in the middle, we have the neox system. This system is controlled by this sensor head here that has 3 different technologies embedded in it. That's why this system is the most versatile system in the market right now. Next to it, we have the neox 5-axis. This system has the same sensor head as the neox, but with this rotational module you can see here. These two systems are more focused in measuring roughness in the sub-nanometer, nanometer, and micrometer range, but also it can be really useful to solve many other applications, as it can be volume, a step height, critical dimensions, and so. Then we have the S-wide here. This system is more focused on big samples and batch of samples, and it's more for the millimeter range surface roughness and for doing some critical dimensions on the surface. And finally, we have the S-Lynx 2. This is the low-cost solution for the neox system. So the system that I want to talk with more details today is the neox 5-axis. And as I told you before, this system has 3 different technologies embedded in the sensor head. First of all, we have the focus variation technique here in green. With this technique, we can measure really good shape and form of rough surfaces and big samples. It's also really useful to characterize high local slopes, and it is the fastest among the 3 of them. Next to it, we have confocal in blue. This technology has the best lateral resolution of all, and that's why it's the best one to measure small features, also to measure surface finish because we need a good compromise between lateral and vertical resolution, and to measure the shape and the form of shiny surfaces or smaller samples. And finally, we have interferometry in purple. With this technique, first of all, this is the one that has the best vertical resolution of all. And again, that's why it's the best one to measure small features, in this case in the Z scale, and also to quantify surface finish. This system also has this rotational model you have here. This allows us to place the sample and to move it in 2 additional axes. At the rotational stage, in which we can rotate the sample up to 360 degrees, and the elevation axis, which we can move it up to 140 degrees. This is really helpful and also allows us to measure the full 3D of cylindrical samples, as the one you can see here, but also to place the sample in specific positions so that we can reach maybe difficult to access areas in which we need to quantify, for example, the roughness or the waviness or any other dimensions you might need. But what can we solve with this system within the gear market? So here you can see the neox 5-axis I have right next to me, and the one I'm going to use for the demonstration I'm going to do later. And also here you can see the gear that I'm also going to use. So as I mentioned before, one of the main applications of the 5-axis is doing a full 3D, measuring the form of cylindrical samples. For gears, it can be a really useful tool for many different applications. For example, it can be really useful to quantify and do a wear analysis of used gears for quality control. It can be also useful too to create a CAD file from a manufactured gear in case you don't have that CAD file. And also right now, a PhD in University of Nottingham is evaluating the system to see if it's a good option and a good solution to do gear measurement and, for example, quantify the pitch of the gears. And how do we do that? So first of all, we need to choose technology. In this case, focus variation is the proper one as it is really fast, and these samples usually are quite big or can be quite big. And also because we want to measure the form, and well, as I mentioned before, this technology is the one that best does it. So then here, this is the Sensofar. This is the acquisition software for the neox 5-axis. And basically what we're going to do is the system is going to rotate the sample 360 degrees, and it's going to measure in different regions in order to obtain individual field of views. For example, here you can see how the system is measuring and also rotating. You will see that later on the demonstration too. But the result is these individual field of views. As you can see, there's an overlapping region between them, and that's really important because then the software is going to merge them to obtain a full 3D. This full 3D can be exported in a cloud of points and also in a mesh and in different extensions as you think it's best for your application. As I mentioned before, this sensor head has multiple technologies. This is a strong point of our system, but in this case, in the form analysis of gears, having confocal and focus variation gives us a lot of versatility because it allows us to measure a wide range of sizes of gears. For example, with focus variations, we have been able to measure a gear with a diameter of 120 millimeters, but we have also been able to measure a small gear down to 2 millimeter diameter with confocal. So with this system, we not only can quantify the form, but we can also measure the surface roughness in specific positions, as it will be the gear, the tooth of the gear, as this is the contact part, the contact area of the gears. So to do that, in this case, we need to change technology, and we will go to interferometry, as it has the best vertical resolution. And to do that, we will acquire topography, and then following the ISO for surface roughness, we will filter it, basically, with the S filter, F operator, and L filter. I will explain it later during the demonstration, but here you can see how a filtered surface would look like in a gear. Also here you can see a profile and a peak to valley. It's on more or less 1.04 microns. And then here you can see the parameters calculated. In this case, I'm only displaying the height parameters, but if you're interested in having the feature parameters, the spatial parameters, we also can calculate them. So for example, here I will look at the top parameter, the SA, which is the most used. It's 0.16 microns. In that same region, we can also quantify the waviness. So, for example, here you can see a topography again, that's raw data. And to acquire that, I use focus variation, as I'm more interested in the waviness and not such in the micrometer scale of the surface. And we can also apply some filters following the ISO for surface roughness, as the waviness is within it. And we can also calculate the waviness parameters to quantify that. So this will be an overview of our systems, of the 5-axis, and also of the different applications that we can solve. So let's do a demonstration. So here you can see Sensofar. As I mentioned before, this is our acquisition software for the neox 5-axis. And here in the middle, you can see a live view of the gear I'm measuring right now. Before continue explaining the software and also doing the demonstration, I'm going to change the camera so you can see the neox and also the gear and how it's going to move the gear at all time. So now you can see that in the live view we are focused in the top of the gear. You can also see it there, and we can move in Z and focus in other parts. For example, here I'm more focused on the slope of the gear, but I can also rotate the gear and keep going down until I'm in the bottom. So the first measurement I'm going to demonstrate today is a form measurement. So to do that, we need to choose focus variation. You can see that here it's already selected as we are in the green icon, but if you need to change technology, it's as easy as switching between icons. Then the lens I'm using is a 5 epi lens. This is because it has a wide field of view and it's perfect for this sample. And also, if you look at here at the video, you can see that the lens is covered by a ring light. This ring light allows us to get more light here in the slopes, because if we reduce it, you can see that, for example, right now we don't get signal from that. So let me upload again. Okay, so the measurement I'm going to do, I'm not going to do a full circle, but I'm going to only measure a section of 15 degrees. This is because doing a full circle can take up to 13 minutes in this sample, and we don't have that time. So I'm going to click acquire here, and while the measurement keeps going, I'm going to explain you a little bit. So basically, here is the 5-axis part, in which I already have all of the settings saved in a recipe that's called webinar gears. So that's why I don't need to do anything, but here I have set the light settings and also the Z range that the sensor head needs to move. I've also set which is the rotation that I want to do in the section measurement. As I mentioned before, 15 degrees is that option. And then, given that information, the software calculates automatically how many measurements it needs to take to cover the whole area. To do that, it uses the information of the section that we're going to move, but it also uses the information of the diameter of the piece. In this case, the diameter of the gear is 75. And finally, use the overlapping percentage that we have set on that measurement. In this case, is of 20%. So as you can see here, well, right now we are at the last measurement, but the system rotates a little bit. You're going to see it, well, it has already happened, and then the sensor head moves from bottom to top to scan the whole part. Once all of the measurements have been done, a merge window will pop up, as you can see it right now, and we need to choose which is the acquisition settings we want to use. I'm going to use the default ones, the system ones. We can see the measurement time. It has taken 1 minute and 19 seconds. We have measured 5 fields of views. Then it's important to do a data alignment to make sure that the merge will be as best as possible. And then let's do the merge. To do that, I'm going to do a sampling of 25 microns. This is because this sample is quite big and we don't need that much resolution to do a full 3D, and also because I want to show it to you as fast as possible how a merge is done. So here in the middle, the gear will appear. Well, in this case, as we only mentioned 15 degrees, it will be 1 or 2 teeth. Then, once it has merged, we can send it to external analysis software, as it can be Geomagic, GOM, Polyworks, to do a full 3D. Well, full 3D, not to do GD&T, for example, another kind of analysis. So this will be our measurement. You can see it looks quite good, but let me show it to you also a measurement of the full gear. So this will be a circle on a gear. You can see there is also a cloud, well, not a cloud of point, but a mesh. You can see it right here. So this will be for the 4 measurement, but we can also measure the surface roughness on, for example, in this part here. So to do that, I need to change magnification and technology. I'm changing magnification and I'm going to go to a 50 magnification, as we need more lateral resolution to quantify the micrometric scale of the surface. And also I'm going to change technologies to confocal, because it has the best lateral resolution of all, and we need a good compromise between vertical and lateral to properly quantify a surface, well, to properly quantify the surface roughness. Also, I'm going to do another thing, is that this gear has been used, so it's quite dirt. So I'm going to try to find one of the two that it's more clean to measure the roughness. So now I'm going to try to focus there, and I'm going to go down until I focus on the surface. So I'm still going down, and here in the live view, you can see that there's this red spot. This means that the light is saturated and that we are getting closer to the surface. So I'm going to keep going down. Okay, now I'm really close. And this will be the surface. It's a bit blurred because I'm a bit out of focus, but this will be it. So again, I'm going to upload the recipe I already have. With the proper light settings, you can see that it has changed, and also with the proper G-scan we need to move. As I'm using confocal, I'm going to change the visualization to the confocal visualization, and as you can see, we only get signal from the parts that are in focus. Right now I'm moving up. This is the top of the surface, and this is the bottom. This is because the 2D is a bit tilted too. I've changed to this part of the gear because for quantifying surface roughness, it's really important to have the surface as perpendicular to the optical axis as possible. That's why we need to focus on that, And that's also the reason why we need to choose a 50x super long working distance instead of a regular epi lens. So now I'm going to click acquire. Now the measurement is being done. And this will be our result. We can see that the topography is a bit tilted. So first of all, we are going to apply a form removal. Now it's completely flat. Also here in these parts, we haven't measured enough points. That's because these parts are vertical walls. So we can also apply a restore. And this will be our unfiltered data. But if we want to measure surface roughness from that, we need to come here to the parameter section, choose the ISO 25178, that's the ISO for surface roughness, and we just need to click here to select which are the parameters, which normally the default values are good enough. Getting more into details here, we're basically applying first of all an S filter with which we're going to remove the micro roughness of the topography. Then here we will have the F operator to remove the form. In this case, it's not necessary because I already applied the form removal. And then here we have the L filter to remove the waviness. And here you can see that we are only keeping the surface roughness of it. And this will be our output parameters. So we have SA, which is the most used parameter, also SZ. And I'm going to save the values. So as you can see, the surface has not been modified, but we have the results calculated here. I've done that because I also want to show to you how we will calculate array. So I'm going to make a profile here in the middle. And here at operators, we also have the ISO for roughness profile. So again, here you can see which is the waviness of this profile and here the roughness. I'm going to click apply, and here we're going to see which are the roughness parameters. So we have an array of 0.3 microns. A very interesting thing is that we can move the profile along the surface and these parameters are going to change. So we can in fact have the roughness parameters of different sections at the same time. So this will be the demonstration. Thank you all for being here. And if you have any questions, do not hesitate to ask later. Thank you.